Okay, next up, Lorenzo Gazzella will talk to us about calculational design of incorrectness separation logic.
Okay, thank you. Today I'm going to present our ongoing work on systematic design of incorrectness separation logic. That is a joint work with Roberto Bruni and Roberta Gori. So we start by defining the problem. The problem is that often proof systems are designed ad hoc for a specific semantics. So we set the theory of the logic, and then we try to set up the inference rules ad hoc for that theory. But this could be challenging, and there is no guarantee that we obtain a well-designed proof system. One approach that has been proposed is the calculational design by Cousteau. That gives a general recipe to derive a proof system for correctness and incorrectness analysis directly from the semantics. The problem is when we deal with heap manipulating programs, we don't have the locality principle that is the core of separation logics. In fact, in separation logics, we would like to have axioms that focus on the minimal amount of information and to derive, to execute the command. And then with the frame rule, we would like to enable the scale of the reasoning. So for example, in the axiom on the left, we have that P skip P as a global precondition. And in separation logic, we would like to have axioms like in the right axiom that focus on the discrete amount of information regarding the heap. So we get emp skip emp. That is the axiom of incorrectness separation logic. So our contributions is first we design a systematic design of program logic. And so by exploiting some closure property of the semantics, that for example could be the additivity, the weakening, and the strengthening of the precondition, postcondition, and the locality principle, we derive the axioms of the logics. So the process with this approach is that we justify or we improve some existing ad hoc axioms. And then for the case of heap manipulating program, we have axiom that focuses on the minimal amount of information for that specific atomic command. And then as a last step, we derive a more inclusive set condition for the frame rule. The second contribution is the application of this systematic design to separation logics. And the first one is the under-approximation logic, and we apply it to ISL and its concurrent version. And we improve the expressiveness of the proof system. And then we are trying to apply the systematic design also to over-approximation logics, but it is an ongoing work. So the systematic design follows some steps. We first define the semantics of the logic. Then we identify some closure operators. And each closure operator induces a partial order. And the meaning is that an element is smaller than another one if we can recover the second one, starting by the first one, and using some closure operator. And then we define a notion of minimality induced by the closures. And so we take every partial order, and then we take the closure, the transitive closure. So the minimal element of disorder will be the axiom of the logic. And the inference rule will be derived from the closure of operators. So we see now the application of under-approximation logics. So we set the theory of our logic that is parametric to the program semantics and to the command, the basic command C. And we say that the theory are the set of valid triples PCQ, where Q is an under-approximation of the semantics over P. And then we identify some closure operator within the logic. The first one says that if Q and Q prime are an under-approximation of the semantics of C over P, then we can remove Q prime and add any P prime and get a valid triple. And this is usually embedded in some existing proof system with the consequence rule. Then we have the second one, that is the one that is embedded with the disjunction rule. And the last one, that is the framing. So we can add, if we have a valid triple, we can add any frame to that variable, and we will see later what is a frame in our setting. So each of these closure operator induces a partial order. And for example, we take the triple PCQ and Q prime smaller than the one on the right, because by applying the consequence, we can recover the right one from the left one. And so the axioms will be the minimal elements of this order. For that specific case of under-approximation logic, we have that any finite application of frame, disjunction, and consequence can be transformed in a composition when we first apply the framing, then the disjunction, and then the consequence. So suppose to have a sequence of closure application in any order. We can transform the application by applying first the frame rule, then the disjunction, and then the consequence. And so by transitivity of the order, we can just apply each of the closure operator only once. And for this reason, we can define a relation that in one step summarize the transitivity closure of the union. And we get this new order that says that a valid triple P1 CQ1 is smaller than another one if we can find a frame that we can add to P1 and Q1, and if we can find a valid under-approximation triple that we can add to P1 star R, and then P is the triple on the right can be recovered by the consequence rule from the left one. So the minimal element of this new order will be the axiom of our logic. We see now what is a frame in our setting. We define an heap as a partial function from location to values with bottom. And the store, that is a total function from a set of variables that are the program variable, and then a set of auxiliary variables. Then the state is any pair of state and of store and heap. And then the possible frame that we can use are those that does not constrain the program variables. So informally, what we express is that the frames can only predicate on the auxiliary variables. And the auxiliary variables are never modified by the programs. So what we get is a semantic proof system that says that any minimal triples is a valid under-approximation triple. And then whenever we have a valid triple, we can add any frame that we take from the set that we defined before and still get a valid triple. Then we have the disjunction and the consequence that are derived by the closure operators. And this construct a sound and complete proof system by construction. So the setting is parametric to the semantics of basic command. And here we take the semantics of ISL. And what we get is that for this, here we have a slightly different meaning for the assertion emp, and it says that we have a memory is the set of every memory with an empty heap, and where for each program variable we have a parametric variable that is equal to the variable x, and so we get this is a subset of the derived proof system. For the skip, for example, we start with an empty heap, and then by executing skip we get an empty heap. And for the allocation, we start with an empty heap, and by allocating x, we have that x is pointing to something. Then the frame rule says that we can take any frame that does not speak about auxiliary variables. And then we have the rule of exist that we see now. So we see now that the frame rule on only parametric variables can constrain also the program variables. So here we have this example. We start with x equal to x prime, and then we execute the skip. We apply the axiom, and we get x is equal to x prime. Then by the framing, we add that x prime is equal to 5 to both sides. And then by the rule of exist, we remove x prime, and we constrain over the possible program variables. And this is a triple that we can derive in our proof system, that it was not derivable in ISL. And this because when we execute this command, we cannot frame out the heap that is speaking about x, and so we cannot apply any of the axiom. Then we try to apply our systematic design to the semantic of the concurrent version of ISL. And since it lies in the theory of under-approximation logic, with a slightly different notion of the store, that is a partial function like the heap, and so as a consequence, a different notion of the separating conjunction. But what we get is that we can reapply the previous methodology, and so, for example, what you get is that for the allocation command, in the original proof system, we have that in the post condition, we have an existentially quantifier only over the possible location. And of course, since we don't have an infinitary disjunction rule for this is a source of incompleteness. And the axiom that we get by minimality, it also quantifies existentially over the possible values that the variable x is pointing. So what we defined is a general methodology that is applicable to different semantics and assertion languages, and that can give some feedback on existing proof systems. As a future works, we would like to explore the over-approximation logic, to apply our strategy to over-approximation logic with local reasoning, and to use abstract interpretation to account this procedure. And then finally, we would like to apply our methodology to logic for backward reasoning. And thank you for the attention.
Okay, we have a few minutes for questions. Patrick?
So, in your completeness proof, you must exhibit what are the auxiliary variables that you need somewhere. Because you say there exist auxiliary variable, but should I take 142? And so the completeness proof must give you the necessary auxiliary variable, and can you characterize that?
Yes, but we assume that we have an infinite amount of auxiliary variable, and in the axioms are set to be equal to the program variable. So I think that it characterizes the possible auxiliary variables.
In the book, there cannot be infinitely many auxiliary variables in the end.
But they are bounded from the program variables. I don't.
Yeah,
Maybe.
there's one for each program variable, right?
Yes.
Any further questions? We still have 1 minute. Radu?
There were a bunch of talks earlier that presented other logics. Did you feel that you could apply your methodology for any of the ones that you saw today?
I don't know. Hopefully.
Okay, thank you again.